Hello, I'm Ajay Chandra from Integrated MSc Physics, and I'm going to present a PPT file on the topic of LVDT and its characteristics. This is the presentation given under the course of PH 310 Applied Instrumentation, and it is CWS presentation. So let's begin. Uh, the contents of these presentations are as follows. First, we will define what exactly it means by an LVDT, the full form of it, and the expandable meaning, and what are the principles behind it. Then the construction, principle and working characteristics, advantages and disadvantages, and then we will show some applications of it which is being used in the worldwide in various fields of engineering. Then finally we will give the idea of the linearity of the system. So what exactly is LVDT? If we can expand the full, if we can expand the meaning of LVDT, it converts into linear variable differential transformer, whose purpose is to convert a straight line motion or position into an electrical signal. The basic purpose of any transducer is to convert any physical change into an electrical signal, and so LVDT does the same. The thing is, it converts straight line motion or the displacement of any rod or something like that, a moving core, into electrical signal to generate any meaningful outcome of that change in the variable. So it consists of primary along with two secondary coils and a movable core made up of ferromagnetic material. As being a secondary transducer, the physical quantities such as force, weight, tension, and pressure are first converted into linear displacement by primary transducer, and then LVDT gives the reading of the change in these quantities in the form of electrical signals. So by this LVDT we can measure force, weight, tension, but it cannot be directly measured. First we have to convert the physical quantities into the displacement into the linear displacement by the transducer, and then the LVDT converts the displacement in that transducer into the meaningful electrical signal. Speaking of electrical output, it's actually difference in the voltage produced on the two secondary coils. This is the basic appearance or the basic diagram of the LVDT, which shows that it contains two coils. These two coils are the secondary coils, and in the middle, this is the primary coil, which is being wounded on the solenoid or moving core, which is being moved inside the hollow cylindrical shaped coils from up to down or from left to right, and the displacement of this inner core produces the change in the flux, which we will show on the later slides. So the basic construction of the LVDT is a typical LVDT consists of a hollow cylindrical core made up of ferromagnetic materials such as iron or nickel, and two secondary coils along with the primary is wound around the core. The secondary coil is placed symmetrically on the either side of the primary coil, which is at the center of the core. These coils are typically non-magnetic in nature, which are free to move axially inside the core. The outer two ends of the coils are fixed so that it can allow the fixed movement of the core inside the coil, so that it can be used to translate the linear motion into the change in the position of the core. So we have to fix the two other coils, the two secondary coils at the end of the transducer to maintain the rigidity of the system to and to freely move the iron rod within the hollow cylinder made by them. So this is the diagram. This is a hollow cylinder. This is the ferromagnetic core, and these are the coils which has been wounded around it in a given rigid structure. The main principle and working of any LVDT is when an AC current is applied to the primary coil, an electromagnetic field is generated around the core, including an AC voltage in each of the secondary coil. The amplitude of the voltages induced in the secondary coil depends on the position of the core relative to the coils, and these voltages have opposite phases. The difference between the voltages in the two secondary coils is proportional to the position of the core, and making the LVDT a highly accurate and reliable way to measure linear displacement or positions. So in this we can generate any secondary any output in the form of EMF. The form of the EMF is E1 minus E2, where E1 and E2 are the corresponding EMF generated in the secondary coils S1 and S2 respectively. The difference of them will be the output of the LVDT. The movement of the rod inside the cylinder leads to the following scenarios. If we move the rod towards the secondary coil S1, then the flux in that coil will be larger, leading to the greater EMF in S1, that is E1 greater than E2, making the difference E1 minus E2 positive. The differential output is positive, meaning the output voltage E will be in phase with the primary voltage. So here is the diagram of it, which is shown in the left, in the right hand side. We can see that if we move the iron rod towards the secondary coil S1, then the flux in the S1 will automatically get amplified due to the magnetization of the core. Hence, the flux in S1 will be greater than the S2. Correspondingly, EMF will be the same. So, E1 minus A2 will be a positive number, which can be interpreted as that the meaning of it, like the phase of the output voltage is in relation with the input primary voltage phase. Second, the second case will be when the core is placed exactly between the two coils at null place, then the flux in both are same, making net EMF E to be zero or non-differential output. So the second case would be that if the core is in the center, then we can say that the either side of the coil has the same EMF, and so the difference will be like zero. So the output of the LVDT will be zero, or the lowest possible value. And lastly, when the core moves towards S2, then the flux is in it will be larger, meaning the E2 is greater than E1, making the differential output E in negative or out of the phase with primary voltage. So this is just the opposite of the first case. If you move toward the S2, then E2 will be greater than E1, and making the E, which is the output of the ability, to be negative, and so it means that the output voltage in out of phase with the primary voltage. The characteristics curves of availabilities are as shown in the figures. Output voltage versus core displacement. The value of change in the voltage will be either negative or positive, is proportional to the amount of movement of the core and indicates the amount of linear motion. The output voltage of an LVDT is linear function of core displacement. Figure 3a shows how the magnitude of the differential output voltage E varies with the core position. The value E at maximum core displacement from the null position depends upon the amplitude of the primary excitation voltage and the sensitivity factor of the particular LVDT. Figure 3c shows that the output voltage of an LVDT is linear over its core motion, and but that the sensor can be used over an extended range with some reduction in the output linearity. Now, some advantages and disadvantages of the LVDTs. LVDTs are highly accurate in measuring the change in measuring the fraction of changes in the physical quantities, because it is just as because it can be measured through a variety of various ranges of the distances over a short interval of short distance value. So which means that it is highly accurate over the small values of the distances, which gives it wide range of operation, low hysteresis losses, low friction losses, no non-contact measurement. Non-contact measurement is required for some of the sensors to be measured, because some sensors cannot be directly touched by the transducer, or we can say that it can be damaged. So we so it LVDT ensures that the that the measurement can be take place non-contact with the sensors. Simple construction, direct conversion into electrical signal, and fast dynamic response. It has several disadvantages too because it involves the solid iron core, so it is of the high cost in measuring in putting in into assembly, and coils will be costly, so it is highly costable. Second, it is affected by the string magnetic field, which is the leftover magnetic field over the from the other instruments in the room, and the temperature changes can also affect its productivity. Second, the last is motion is very limited to a confined value of the distance. It cannot be moved to a very large distances because the coils can not be because it will be highly costable to do so. Some of the applications of the LVDTs are as shown in the figure. This is a simple weighing machine which we used in our regular homes, which contains a spring in the form of zigzag pattern, and the weight of the source or the measurable quantity can be applied on the top of it so that it can balance the springs, and even a fraction of change in the displacement of the spring can lead to a value of the change in the magnetic field of the LVDT, which further generate the change in the EMF, which can be measured directly by the output of the LVDT. As we seen that LVDT is highly sensitive and can detect even a fraction movement in the spring of the order of m or centimeters. So it can be used in weighing machines to measure the weight. Some principle, the same principle can be applied in another application of seismic monitoring, which is used to measure ground displacement during earthquakes. So during earthquake, we have small displacement of the ground surface. So it can be directly linked to the LVDT, which can measure or detect the movement of the surface and can produce electrical response. Linearity of the system. There are several synchronous demodulators to obtain the core position signal. Traditionally, these are provided by an analog multiplier and low-pass filter to extract the core position signal from LVDT signals. However, the core position signal obtained from the demodulator is narrow due to the structure of the LVDT. The measuring range of LVDT offers a narrow range due to its non-linear transfer characteristics. It can be seen that the linear measuring range of LVDT is linear only in the range around zero crossing of its transfer characteristic curve. The linear measuring range of the LVDT can provide a wide measuring range to meet such a requirement by increasing the size of the LVDT, which results in the bulky structure of the LVDT. These are some of the responses. These are some of the references from which I have extracted the information, and these can be used by me. These are used by me to make this PPT more attractive or more flair to add more flair to it. So thank you.